Shall I start?
Yeah, madam, please.
A very good evening to one and all present for this webinar. I, Professor Kajal Paviskar, extend a warm welcome to today's resource person, Dr. Krishnamurthy Bhatt, dignitaries, all the respected principals, staff members, and of course, dear students on the behalf of Kekewag College of Pharmacy, Nashik, for this webinar. Kekewag Education Society is a leading name in the educational field in not only Nashik, but also all over India since past 50 years. It was established by the visionary leader, late Padma Shri Karmavir Kakasaheb Wagh. There are total 36 institutes running in 9 different campuses and engaged in studies from KG to PhD in various fields. Kekewag is known for academic excellence and is most trusted brand in education. Dear attendees, this 2 days webinar has been arranged to address most important part of our pharmacy curriculum, that is spectroscopy. Spectroscopy is a tool for studying the structures of atoms and molecules. It is also a precise analytical method for finding the constituents in material having unknown chemical composition. Spectroscopy is involved in assays as well as other quality control parameters of pharmaceuticals. Thus, to make these techniques more simpler and to provide thorough understanding of UV visible spectroscopy and spectrofluorimetry, we have a very highly intellectual and distinguished personality, Dr. Krishnamurthy Bhatt. So I would now request our principal, Dr. K.S. Jain sir, to welcome all the guests. Please, sir.
Thank you, madam. Good evening and welcome. I welcome my dear friend, my very old friend, Dr. Krishnamurthy Bhatt, and my host many a times when I used to visit regularly Manipal to his college in connection with some academic activities. Dear friends, this COVID-19 has been a very great pandemic, and it has created havoc in all walks of life, and it still continues, and we don't know till how long it will continue. It has eaten up a lot of time since March as far as our academics is concerned, and we don't know, it may take the full term also. Anyway, the life has to come to normal and we have to proceed further. So teaching learning activity in different mode has started, and that is online teaching or learning. Initially in month of March and April we were struggling a bit. Now it has become a routine, but I can still understand that in many colleges, depending on the situation, the geography, the infrastructure, the connectivity and all issues, many places still teaching learning has not picked up to that extent. I was particularly worried about the final year students who have entered final year, and instrumental methods of analysis happens to be one of the very important subject. And incidentally, this UV visible spectroscopy as well as fluorimetry forms the first unit of the PCI design syllabus, which is implemented all over the country for the semester 7th for final year B.Pharm. So I thought at least everybody in final year B.Pharm might have started the teaching with this subject, and by far most of the colleges, I say most of the colleges, not sure all of the colleges, might have completed this syllabus. And while completing this syllabus, there would have been various problems, issues, connectivities, attendance, infrastructure, and also availability. And therefore, I thought it very important to design such a series of talks, particularly relevant and in line with the syllabus content of the instrumental method of analysis, because this is very important subject, particularly for each and everybody in final year. Particularly in the practical life also, you are going to deal with UV in not only in chemistry but other branches also. These instrumental method analysis, as madam said, are very sensitive ways of doing analysis, far sensitive than the volumetric methods. And this particular syllabus, unfortunately, we are in this particular syllabus, it has been so designed that we encounter with it only in the final year. Earlier, we used to encounter it little bit earlier also. And therefore, I am particularly bothered about the students, whether they are my students or whether they are the other students, whosoever are the students, and we are actually striving hard for the student community, and they are the stakeholders. We are doing everything for the students, and students should not suffer. And therefore, we planned these 2 lectures one by one in 2 days. And we are also planning the next part, the second unit, that is IR spectroscopy, and also the other things like flame photometry and nephroturbidometry and AAS, that is atomic absorption spectrometry, which come in the second unit. And then after again in the month of August end, we are planning to go for HPLC. And this entire syllabus then deals with various types of chromatographies. So all in all, this is a very, very important part, very critical part. So either for some colleges, it may help as a revision by a real expert in this field. And some colleges, it may be also the initiation of the topic. So in both ways, it is definitely going to be very, very beneficial. And therefore, I insisted on my colleagues, particularly we are affiliated with the DBATU, that is the Dr. Babasaheb Ambedkar Technological University, which are now having 107 colleges. But we happen to be the first batch in that. So we were 14 colleges. So I estimated at least 500 students may be there who may be suffering. And I'm happy to tell you that these both madams who are coordinators of this, they gave me the figure of 561 registrations. I have been little bit pursuing it very hard. I am talking and pressing the principals, Array, for your students, we have to do something. And I'm very thankful to them that they have given me such a positive and overwhelming response. And I have personally talked with many, and finally the sum total has crossed. And today, just now, many times it is our experience that registrations are not equal to the number of attendees actually, but I am finding it is continuously like corona, the number of attendees is continuously on rise, and it is one by one. Now today it is just now it has reached 213. That is a great figure. And so I deliberately passed some time in showing some videos, because people should not suffer for the initial part. And now, without wasting, I have explained my idea and my philosophy, that why we have taken up this, and we will continue to take this, and our endeavor is to complete this. I will also arrange a few lectures by some experts from Perkin Elmer. I am in talk with them. So one by one we will finish this, then we will also take some other things. We are little bit at forefront of our teaching learning. At our college, we are also on the verge of completing the second unit also. But then let us give back to our colleagues and our friends and our student friends particularly. And therefore, I insisted to the principals that not only you ask your students to join, but you also ask your subject teachers to join. And I am happy, I see few names here in the attendees. They are also joining, and I am definitely telling you, you will definitely not be disappointed, because I know Dr. Krishnamurthy is a very good teacher, and therefore I will, without taking much time, now I will proceed further and request either Pooja madam or Kajal madam, as per the agenda, to take over and take the proceedings further. Thank you very much.
Thank you very much, sir. I would now request my colleague Pooja Magar madam to introduce our today's guest. Pooja madam, please.
Yes. Am I audible?
Madam.
Am I audible?
Yes, madam, you are audible.
Okay. Okay. Thank you, madam. Good evening, all. Myself, Professor Pooja Magar. It is my great privilege to introduce our today's eminent speaker, Dr. Krishnamurthy Bhatt, Professor, Department of Pharmaceutical Quality Assurance, Manipal College of Pharmaceutical Sciences. Our esteemed guest is expertise in the field of quality assurance and instrumental methods of analysis. He is an academician holding more than 17 years of experience, and currently he is working as professor in Department of Pharmaceutical Quality Assurance, Manipal College of Pharmaceutical Sciences. He has completed his doctorate in the year of 2004 from Gujarat University. He has participated in 39th Indian Scientific Expedition to Antarctica to execute a research project which is sanctioned by Ministry of Earth Sciences, Government of India from November 2019 to February 2020. He must be probably the first pharmacist to do so. Sir has established complete bioanalytical laboratory for Manipal, Acunova, KHRSC, and he successfully completed the first US FDA inspection. He received Best Poster Award under Pharmaceutical Analysis and Quality Assurance Discipline at 63rd Indian Pharmaceutical Congress 2011. He also received Indian Drugs Best Paper Award in 2003 in the discipline of Pharmaceutical Analysis. He also has received Distinguished Alumni Award of JSS College of Pharmacy, Mysore, Best Paper Award at Annual Conference by JSX, Japan. Then he also received a travel grant by International Society for Study of Xenobiotics to attend 3rd Asian Specific Regional ISSX meetings. He received Best Paper in the field of pharmaceutical analysis, which is published in Indian Journal of Pharmaceutical Education and Research in October 2013. He has attended more than 10 international conferences and workshops. He is also having life membership of many professional bodies like APTI, IPGA. He has received research grants from European Union under MMRDC, from Government of India under AICTE Modrops, and from International Society for Study of Xenobiotics, totaling to more than 1.5 crore rupees. Sir has total 41 publications, which include 12 national and 29 international publications. He has presented more than 50 papers at various national seminars, symposia, or workshops. There is much to say about Sir, but due to time constraint, without much ado, I would like to request Dr. Krishnamurthy Bhatt to commence the session. Please, sir. So you can start with the session.
Yes, sir.
Can you see my slide?
Yes, sir.
Yes.
Yes.
You can now
Okay.
expand them. You can go to the slideshow.
Okay.
At the bottom.
Right.
Yes, sir. You may start.
Okay. Thank you, Jain sir, for that nice introduction and the what do we say, introduction to the topic and the noble objective with which these things are being conducted, and Pooja madam for that nice introduction. Now coming directly to the topic of today's webinar, that is UV visible spectrophotometry as per ACT syllabus. Now this is what is the syllabus. All of you can see that syllabus in your screen, and I'm sure many of you will also have the copy of it. Now essentially, as sir has told, I may not concentrate much on the syllabus part. I would try to add more on what is not there in the syllabus, but very much related to the topic. Now, to start with, okay. Now, UV visible spectrophotometry is something which is there for long. Now, it is there, I mean, especially from last 35 and odd years, this has become a very, very important analytical tool. And that is the reason. And it has also its importance is increasing day by day. And most of us are not using this technique to its full capacity in research. So that's one of the reasons which I thought I would, at the end of this talk, focus more on the application, how this can be used for the research part. The advantage of UV is it's very simple and versatile, cost effective. You don't need huge investment on instruments or on the solvents and other things, with the same level of accuracy what you get in chromatographic methods, except for the fact that the sensitivity of this may not be as high as that of chromatography, but otherwise it has a lot of applications, and that's a reason why we still study this, why we still use this in large part of research and things like this. Essentially, UV is absorption spectroscopy. Now, what is absorption spectroscopy? Absorption spectroscopy is where the light or the electromagnetic radiation, many times I and most of us use light in what do we say, in connection with EMR. When we say light, it need not be visible light in the real sense of its wavelengths, but it is electromagnetic radiation we talk about. It consists of discrete particles. Now it's a old theory, all of we know it, right? It's a both wave theories and quantum theories on radiation, etc. But for the sake of understanding this topic, we will use the photon theory to a larger extent than the wave theory. Now, photon consists of oscillating electrical and magnetic fields which are perpendicular to each other. Please remember this. Now, when we are talking about this is what represents the electromagnetic radiation. Of course, this represents the whole wave, and this is the variation of electrical field, okay, the vibrations in electrical field. And the blue one here, what you can see is the magnetic field, which is perpendicular to the electrical field. This magnetic field is perpendicular to the electrical field, and this shows the vibration, the magnetic vibration. Okay, now this, of course, to monochromatic light I'll come later. And see, this is what you need to envisage when we are talking about later on, when it comes to some other techniques. We will talk about plane polarized and unpolarized light, right? Plane polarized light means the plane of this vibration is what we will be talking about later. Not me, but somebody else. In other techniques, we use some radiation called as plane polarized light. This is what is important, not the wavelength or the frequency. Okay, please remember that very well. They are two different things. Monochromatic light is different from plain polarized light. That's what I essentially want to insist at this point. Many times, as students, we get confused that plain polarized light, monochromatic lights are same. They are not. Okay, now coming to the next part. The light wave is essentially characterized by some of its values. Frequency is one of them. Frequency is the number of times an electrical field oscillates per second, and it is given as hertz. 1 hertz is nothing but 1 cycle per second. At least, if not with the light wave or radiation, EM electromagnetic radiation, you might have heard this with sound waves, right? Most of us hear this FM radio stations. They say 98.3 megahertz, 95.3 megahertz. That is what is the frequency at which those sound waves of those radio stations are transmitted. So similarly, I mean, sound and light waves behave very similarly. Probably again from the perspective of UV visible spectrophotometry, frequency is not very important, but wavelength, yes. Wavelength is one very, very important aspect what we are going to talk about in most of these spectrophotometric techniques, whether it is absorption or emission. So this is what is wavelength, the distance between two consecutive crust. This is called as crust of the wave, and this is called as the trough of the wave. Either two consecutive word again is important here. Two consecutive crust or two consecutive troughs is called as one wavelength, right? This is measured in nanometers and designated as lambda. Each wave will have its own energy, and that energy is given by hc upon lambda, where h is Planck's constant. Now, if you see this equation, it is very clear to us that higher the wavelength, lower will be the energy, right? Or shorter the wavelength, greater is the energy. Now, each molecule, when we talk about, consists of multiple energy levels. It is not just the electronic energy, right? There are rotational energy levels and vibrational energy levels apart from electronic energy levels. What actually happens is, this is the ground state. If we consider this as the ground state and this as the excited state, the electron moves from ground state to the excited state, and that will require some energy. Now, many of us know this. Any function requires any energy, right? Or when energy is given, the work is done. Higher work requires higher energy, right? And this movement of the electrons to different electronic energy levels would require higher energy, and that is why UV, and we also see shorter the wavelength, higher is the energy. That is why this type of transition is seen only in UV, only when the compound is bombarded with UV radiation, not with longer wavelength, lesser energy radiation, right? Lesser energy radiations may bring in some vibrational and rotational energy changes, which of course will be dealt later on. This also is used for analytical techniques, that which will be dealt later. Now, having said this, from one energy level, the electron jumps to other energy level, from stable ground state to unstable higher energy state. So when you envisage one such thing, what we can think is that energy should manifest as a peak like this, right? Because it is single step jump from here to here. So this is what a peak should look like in molecular spectrum. But unfortunately, that is not happening. How UV visible spectra looks most of us have seen this, is something like this, right? It's not a line spectrum, it's a band spectrum. Now, why so? The reason is, if you can see this, all these energy levels. Now, atom cannot move from say here without passing through rotational and vibration energy level to electronic energy levels, and there will be multiple atoms undergoing all these transition at any given point of time, and that's the reason why you see a molecular spectra as a band spectra rather than a line spectra. Yeah, right. Now, how does this movement of the electron happen? As all of we know, there are 3 types of bonding orbitals and 2 types of anti-bonding orbitals, that is sigma, pi and n bonds as bonding orbital, and sigma star and pi star as the anti-bonding orbitals. N star is not an anti-bonding orbital, please remember. N is a bonding orbital, N star is not an anti-bonding orbital. So we have 5 sets of them. So the excitation of the atoms, I mean the electrons can happen in any of these combinations: pi to pi star, sigma star, pi star, n to sigma star, and n to pi star. Okay, these are the 4 possibilities. Now, sigma star and n sigma star, these are the 2 which requires higher energy levels, and that is why higher energy means the lower wavelength, shorter wavelength, and that shorter wavelength comes from maybe vacuum UV, anything lower than 200 nanometer wavelength, and that's why generally this is seen only in saturated compounds, this type of transition. That's why they don't show in the typical UV spectrophotometer saturated compounds. That's the reason they don't show much of an absorption, whereas pi to pi star and n to pi star are the one which requires comparatively less energy, and that's what which happens in conjugated systems, and that is why we see those things happening in conjugated systems. Now, how does this manifest? What is this absorption takes place essentially by 2 types of by the chemical structures known as chromophores. Chrome, as all of you know, is color. So chromophore essentially means color varying. What is this chromophore? Chromophore is a functional group which exhibits a characteristic absorption spectrum in UV or visible region. Nitroso, azo, azoxy, azoamino, carbonyl, thiocarbonyl, etc. are some of the common chromophores. Now, these chromophores in isolation may not be of much use to us pharmaceutical analysts, but when they are combined with other chromophores of same nature or different nature, any of them is okay. The bonding and other things are chemically driven, but when these chromophores are combined to form a compound, those chromophores will have their absorption in UV range, and that absorption would be obviously the wavelength at which this absorption happens would obviously be different than the isolated or the single chromophore, and that is why the organic compounds, conjugated organic compounds, absorb UV radiation at very specific wavelength, which is in turn related to the energy requirement of that molecule. Now, apart from chromophore, there is something called as oxochrome. What is this oxochrome? Oxochrome is per se will not absorb UV radiation, that will not show any absorption. But when it is attached to a chromophore, that will show a huge difference in the absorption of the chromophore. Groups like OH, NH2, CH3, NO2, etc. act as oxochromes when they are present as the the functional groups in the molecules, that will affect the wavelength at which the compound absorbs. Of course, all these things I'm only touching them very superficially, because in the theory class and regular classes, the teachers are going to deal with them in more detail. And this effect of oxochrome on the chromophore, on the absorbance by a chromophore, depends on its polarity. And it is possible to predict, especially the effect of weak weakly polar oxochromes on the absorbance of chromophores, and strong chromophore, strongly polar, becomes a little unpredictable because of many other factors which are involved. And all these things probably you will study in Woodward-Fisher rules and Fisher-Cohn rules when you are going to study about the homonuclear absorption and things like this. There are the lambda max and the compound, or the structure elucidation can be done using UV visible spectrophotometer, and the lambda max can also be calculated. Now, there are largely two laws which govern the absorption, UV absorption phenomenon, which are called as one is called as Lambert-Borger's law. Now, it may look slightly unfamiliar to you, the Lambert-Borger's law, because there are reports which say Borger was the first one to identify the phenomenon of light absorption, and he gave law in 1759, but that largely went unnoticed. And then Lambert was the one who gave a mathematical form to that, and then people started using it. That's why it is largely known as Lambert law, but essentially it is Lambert-Borger's law. That apart, what does Lambert law says? Lambert law says when a monochromatic light passes through a transparent medium, layers of equal thickness of that homogeneous absorbed medium absorb equal proportion of incident radiation. And Beer's law says the fraction of the monochromatic radiation energy absorbs on passing through a solution is directly proportional to the concentration, right? Now, equal thickness is nothing but thickness of the medium which absorbs, right? And both these laws are combined to form a very, very popular and most widely used law in spectroscopy called as Lambert-Beer's law, or Beer's-Lambert law, which says quantity of light absorbed by a substance dissolved in a fully transmitting solvent is directly proportional to the concentration of the substance and the path length of the light through the solution. And the mathematical equation for this is given by a simple equation, that is A is equivalent to ABC, where A is absorbance, B is capital A is absorbance, lowercase a is absorptivity, B is path length, and C is concentration. If you know any two of them, and you can always calculate the third. Now, coming to instrumentation. Instrumentation, we will have light source, a monochromator. Light source largely used in case of UV visible spectrophotometer is hydrogen deuterium lamps. But some of the instruments will also use tungsten lamp for visible region. And monochromator is the one which converts this multiple wavelength or polychromatic radiation. Polychromatic radiation is the radiation with multiple wavelengths. Many wavelengths of the radiation is. So that is converted into monochromatic with the help of monochromator. There are various types of monochromators, and slit is one of them. Prisms are more commonly used, and the latest instruments, like spectrophotometer, is used gratings, different types of holographic gratings as the monochromator. Now, reference cells, when it comes to UV visible spectroscopy, I mean, it has to be transparent, and glass is not transparent to UV. So in UV, we use quartz cells or silica cells sometimes, and for visible radiation, you can easily use glass as well. They are generally 1 centimeter. The commercially available instruments supply you with 1 centimeter as a cell, and others are also available, but they are made to order. You need to specifically order smaller or larger size, larger path length cells. 1 centimeter is commonly supplied. This detectors, photocell is the most commonly used detector, but photomultiplier tubes also used as detectors, and the amplifier, the signals produced because from the light on photocell is very weak. They need to be amplified or need to be augmented, and that is done by servometer, and then that signal is fed to the recorders. Recorders can be pen recorders, or most computers which are there can also be used as recorders. They store data, they store the other details of the method, and then it is done. Okay, this is in brief, very brief about your syllabus. It also syllabus says application. Now, as I promised, I will talk for next few minutes on latter part of the presentation on applications of UV visible spectrum. Now, in pharmaceutical analysis, we encounter with two types of sample. One is you have one component, and we need to quantify that component in the given matrix or given sample, and that is that becomes that's the objective of the method. But in many cases, it also happens that there are multiple components. Now, some cases, the multiple components we may have to quantify. In other cases, we may not have to quantify some of them. We have to quantify only one component in presence of many other components. Like if I have to give you a very simple example, if you are doing the assay of an API, then it will be a single component analysis, because we know API is pure. It is only one drug which we'll have to analyze. Whereas if it is a formulation, that is a tablet, capsules, complicated formulations like that, we still need to quantify only that API. But then we also know that the tablet would contain many other excipients like the diluents, or maybe the glidants, and compressing agents, etc., binding agents, so many of them. So in such cases, the whole dimensions of analysis would be different in these two cases. Single component is by and large simple. We can there are 3-4 methods available for the quantification of single component, and one of the most commonly used is using standard absorptive value. Absorptive values are either A 1% 1 centimeter, which is called a specific absorptivity, or epsilon, which is called as molar absorptivity. Now, specific absorptivity is denoted as A 1% 1 centimeter. As the name suggests, it's absorbance of 1% solution in 1 centimeter path length. Right? Again, if you can relate, go back and relate with the mathematical equation Lambert's wheel. It is A is equal to ABC. So absorbance is equivalent to the mole absorptivity into path length into concentration. So we are defining path length and the concentration. So absorbance is absorbed, right? So 1% solution in 1 centimeter path length, whatever the absorbance is given, that is what is called as specific. But only thing is here the concentration is 1 molar solution, right? 1 molar solution. That's A is equal to epsilon BC, when B is 1, of course, and C is 1 molar solution. 1 molar solution is nothing but 1 gram molecular weight dissolved in 1 liter of solvent. Okay. Now both of them are interconvertible, provided we know the molecular weight of the compound. But generally, the this is very widely used method, standard absorptive value, especially specific absorptivity value. That's A1%. That's the most commonly used technique for quantification by UV in most of the pharmacopoeia, whether it is Indian pharmacopoeia or United States pharmacopoeia. They use standard absorptive values. Now the advantage here is you don't need a standard substance. You only need to know what you are analyzing and what is it, A1% 1 centimeter value. The pharmacopoeia will give you the specific absorptive, say 1% 1 centimeter value. So based on that, you just have to measure the absorbance and then convert that into the concentration. It's very simple. Similarly, whereas as it is clear from the value itself, when you use a specific absorptivity, the results would be in terms of the concentration. What you obtain is grams per 100 ml because it is 1%. So the results, concentration, what you obtain when you use specific absorptivity, please remember this, is always grams per 100 ml, irrespective of the quantity of solution what you have prepared. So similarly, you can also use epsilon. Epsilon is nothing but the molar absorptivity. That's absorbance of 1 molar solution in 1 centimeter path length. Very similar to specific absorptivity. The concentration here you get is in moles per liter. Moles per liter, which can be conveniently converted to any other form provided with the molecular weight. Now all these measurements are made in lambda max. I should have told you earlier, but now let me tell you. Lambda max, what is lambda? Lambda max is the wavelength at which the absorbance is maximum. Now you can see in this graph, the lambda max, this point is called, this wavelength is called as lambda max. Now please remember, defining lambda max is very, very important, right? Lambda max is the wavelength at which the absorbance is maximum. Many times, because I have been last 25 plus years of my experience as a teacher, I've seen many times people, whenever you say, what is lambda max? Maximum absorbance. No, lambda max is not maximum absorbance. Lambda max is the wavelength at which the absorbance is maximum. This is lambda max. Okay. Now, why do we measure the absorbance at lambda max? In this case, 500 nanometers. The reason is, if you can see here at lambda max, this curve is slightly plateau, whereas in this other portions or other wavelength, the curve is very steep. Okay, either side of the line. Here it is comparatively flat. Now, what advantage this plateau region of lambda max offers? It offers us one major advantage, that is, even the monochromatic light is not very effective. That is, in technical terms, we call it as broader bandwidth. Right? Bandwidth is depending on the monochromator what we use. Some of the monochromators can have as high as 10 nanometers as the bandwidth. The best ones will have 0.5 nanometers as the bandwidth. What does it mean? If you say the instrument has a bandwidth of 1 nanometer. That means when you select a wavelength of 500 nanometers in the instrument, the radiation would be anywhere between 500 plus minus 1 nanometer. That's 499 to 501. It cannot be exactly 500 nanometer. Okay, and if the bandwidth is 10 nanometers, then it will be anywhere between 490 to 510 nanometers. Better instruments will have, sir, nahi hai na? So okay, can some any of you please tell me whether I am audible?
Yes, sir, you are audible.
Okay, fine. Thank you.
Yes, sir, you are audible now. Okay.
Okay, okay, sir. Now, yeah. So this, if we are talking about lambda bandwidth. So even if the bandwidth is slightly great here, the absorbance values will not be affected to a larger extent. But just on the other hand, you see here, this is 490. Now the absorbance is 489 and 491 would be drastically different than 490. Whereas here 500, 501 and 499, there will be no major difference in the absorbance values. That is one of the reasons why we measure the absorbance at lambda max. Most of the analysis we do it at lambda max. The second reason is because the absorbance is highest here, we get the best sensitivity when we measure at lambda max. Now, if that is not an issue, if we are not very specific about sensitivity, my concentration, say I'm analyzing a 500 milligram tablet, where sensitivity is not a major issue, we can always do the analysis at other wavelength other than lambda max. Please remember this, not necessarily lambda max, but lambda max has advantages. Analysis can always be done in other wavelengths other than lambda max also, provided the compound shows some absorbance at that value. But please remember, if you are using absorptive values, then that is wavelength dependent. So we cannot do analysis 490 and use the absorptive value of 500 nanometers. We will have to use the absorptive value at 490 nanometers only if we are doing analysis at 490 nanometers. That's one thing which we are generally the reported values of absorptivity, that is specific or molar, either of them are at lambda max, not in other wavelengths. Of course, it's not difficult to calculate the absorbance values at absorptivity values at any wavelength of our choice. Now, the next method of quantification is single point calibration curve. Again, this is also many times we have used this. It is AU by AS is equal to CU by CS. Right? That's a simple equation which is rearranged as AU into CS upon AS would give you the concentration of the unknown. U, of course, this unknown I have written here. Standard. A stands for absorbance, not absorptivity, absorbance, and C stands for the concentration. So you prepare one a single solution of a known concentration and measure its absorbance and measure the absorbance of the sample also, and then you plot. So you have two absorbance values and one concentration which you have prepared. So substitute the values, you will get the concentration from the unknown, and then apply the dilution factors accordingly. You'll get the concentration of present in the given sample. But only thing is there are some prerequisites. One is the both solution, that is both unknown and standard, should be prepared very similarly. That is solvent should be same, and the other preparation condition should be same. Preferably concentration should be matching. They should not be too far off from each other. And then the condition, the measurement should be made under similar conditions and same wavelength. And this concentration, this standard concentration and consequently unknown concentration should be within the linearity range of that particular compound in a given circumstances. Now, sometimes what happens, it may also happen that we have not a linear relation. This linearity is not proved or not proportional to the concentration. It does not pass through zero. There is linear relationship, but it is not a proportional relationship. So in such cases, there is another method called as double point calibration. Double point calibration is very similar to single point calibration, but only thing is we use two standard solutions instead of one standard solution. And those two standard solutions, the should be or the unknown should be bracketed between two standards. What does it mean? It means if unknown is expected, if we know the exact concentration, we would not do analysis. If the unknown is expected to be, say, 10 microgram per ml, then two standards should be maybe 8 and 12 micrograms per ml, or 9 or 11 micrograms per ml. Not that unknown is 10 and you have two concentrations at 12 and 14, right? Or 6 and 8. Not like that. The unknown should be bracketed between two standard solutions when we are using double point calibration. Once we take care of that, rest of the things are very simple and very similar to the single point calibration. And the equation is the absorbance of unknown equation is given here. You will find it in many of the textbooks. Now, the other probably most important, most widely used is calibration curve. Calibration curve is where you prepare a set of standard solutions in a range of concentrations, maybe 5, 6, 7, 9 standard solutions, and those 9 standard solutions are from the known standard solutions are known concentration, and then you have you measure their response or measure absorptivity, plot a standard curve or plot a linearity graph between concentration and absorbance, and from that extrapolate the concentration of unknown from the absorbance of known. This is we use very commonly used technique in quantitative analysis, so I'm not going to talk much about this. This is more important, multi-component analysis. Now, many times what happens, that one example I gave you is about the formulation. Formulation will contain more than one ingredient, in which we only need to quantify the analyte, right? The active or the drug substance, which is present in formulation, we need to quantify, but there will be other we may not have to quantify. But the drug the drug formulation, drug product may also be a fixed dose combination where we have more than one active ingredient which needs to be quantified. Or if it is a liquid oral, we may also have to quantify the preservatives which are used. So in all these cases, irrespective what we are going to quantify, maybe one we are going to quantify, more than one we are going to quantify, but the most important thing is there will be more than one component present, and they absorb UV radiation, right? They absorb UV. If they don't absorb UV radiation, we are happy. But if they absorb UV radiation, then the problem comes. The things becomes slightly complicated. But before venturing into multi-component analysis, it's very, very important that we know what are the compounds, at least what are the probable constituents which are present in the sample we are going to analyze. These are the things which may be present. This may have starch, this may have dicalcium phosphate, this may have silicon dioxide, this may have methyl paraben, this may have propyl paraben, etc., etc. That is very, very important. Without that, venturing into multi-component analysis can be dangerous. The results may not be very reliable. Now, what do we assume, or what are the hypothesis which is made in all multi-component analysis? Is at all wavelengths, the absorbance is the sum of individual absorbances. That's one assumption which we make. The other assumption we make is the measured absorbance is the difference between the absorption of the sample and absorbance of the blank. That means the absorbance is contributed only by the components of the solution, not from the solvents of the sample. Right? These two we need to ensure. How can we ensure? I mean, this first one is a reality. The second one is you always take a blank and make it 0. Right? If you are using a double beam UV visible spectrophotometer, then keep blank in both of them, in both cuvette or both sample cells of the instrument, and then make it as auto 0, and only then measure the absorbance, count the absorbance. Now, or again, blank is another important component to get accurate results. Either you can use solvent blank or reagent blank, depending on the situation. If the reagents which are used also is expected to have some absorbances, then it's always better to use the reagent blank than solvent. Now, what are the different methods of multi-component analysis? The simplest is using absorbance correction. This is called as absorbance correction method. What is absorbance correction method, and how do we do that? Now, if you can see, this is the example what I'm putting is ephedrine hydrochloride and chlorocresol mixture. Now, if you see here, say at a wavelength of around 250 here, where the pointer is, all of you can see this pointer, right? Now here we have only ephedrine absorbance, but not chlorocresol. Chlorocresol absorbance at this point is 0, and rest on the points, both of them have absorbed, right? And except here again, when it comes, the chlorocresol has absorbance, ephedrine absorbance becomes 0. Now we need to have the mixtures, only these type of mixtures, where at least there should be one part of the spectrum where only one compound absorbs and the other does not absorb. You need to have something like this. At one point, these are the specific absorptivity values. You need to have one of them as 0, right? Only then we can use this absorption correction method. If all of them have some value here, you cannot use this method. That's what, in nutshell, that's what it means. Okay, now you select two wavelengths. Here I have selected 257 and 279 as two wavelengths. That is 279 is here somewhere, and 257 is here. Okay, and measure the absorbance of two standard solutions, ephedrine and chlorocresol, at two wavelengths, and calculated the standard absorptivity value. That's A 1%, 1 centimeter values. Now the mixture of these two, I measured the absorbance at both wavelengths, that is 279. Mixture, you cannot measure the absorbance of individual components. You have to, because it's already a mixture, you measure at both wavelengths, that is 279 and 257, and these are the values which I got. Now, how do we go about calculating? At 279, we know that ephedrine does not absorb anything. So whatever absorbance value at 279 is only because of chlorocresol. right? And so when we use Lambert's equation, the concentration what we obtain is is that of only chlorochrosol, and chlorochrosol, and the concentration of this, more importantly, is grams per 100 ml, because I am using specific absorptivity. Now, once that is done, here at 279, we have solved the problem. Now, 257, both of them are absorbed, right? So this value is the absorbance because of both constituents. Now, how do I know what is the absorbance due to chlorochrosol and what is the absorbance due to ephedrine hydrochloride? I need to separate this into two parts. How do we do it? We do it by a very simple method, because it is the same solution. We know the concentration of chlorochrosol now. So using that absorptivity values at 257 and absorbance at 257 of the total solution, absorptivity of chlorochrosol, because I know the concentration of chlorochrosol, I use the absorptivity of chlorochrosol to calculate the absorbance of chlorochrosol at 257. At 257, right? So among this is the total of these two. This is from chlorochrosol out of 0.972. So I subtract this from the total absorbance. So that is what I get, and the difference between these two is, in simple terms, the absorbance of ephedrine hydrochloride at 257, right? And once we know that, once we know the absorbance at 257 of ephedrine, we know this is the absorptivity value, that is the A1 per 1 centimeter, and we know the absorbance. Calculate the concentration again in terms of grams per 100 ml. Right, this is very useful method in especially when we have a situation like the earlier one I described, where one of the component has absorbance and other component does not have absorbance. We need to identify one wavelength which meets this criteria, and then the things are easier. Now, other thing, this many people call this a simultaneous estimation, but in the real sense, it's not a simultaneous estimation. Pharmacopoeia also has some of the methods which are based on this, where you extract them physically, you separate two constituents, and then quantify both of them independently, like single component. The other method is simultaneous equation method. This is also called as Virat's method. Virat's method is something you might have heard very frequently and commonly, right? Where you develop equations for the simultaneous equation, for the measurement or for the concentration, calculation of the concentration, right? That equations are available, we will see, but then many times we also end up applying this method indiscriminately. I read a lot of research papers also where this method is very indiscriminately applied. But please remember, this method cannot be applied indiscriminately. We need to apply this method only when the separation is the lambda max of these two compounds is quite far apart, something like this. And if it is something like this, there is a lot of interference. This one is the spectrum of the mixture, right? If there are a lot of overlap, then we cannot use Virat's method or the simultaneous equation method. Please remember, for a given combination, it's not that you can use any method and try to get the results. So that is wrong. Now, the question comes, how do we know how much is the interference of each one of them? how do we find out? So that is done by calculating these two ratios. What is this? This is absorbance of component 2 upon absorbance of component 1, and this is again absorbance of component 1 into the absorptivity of component 1, and these two ratios is something which we need to calculate, right? This is absorbance and this is absorptivity, and in case of this value, it should be less than 0.1, and this value should be greater than 2. That means the lambda max are differing considerably, right? If this condition is not met, then preferably don't apply simultaneous equation method for the estimation of two components. Now, these are the standard formulae which is available in any of the textbooks, where lambda 1 and lambda 2 are the two wavelengths which we have selected. They can be lambda max of each of the components, no problem with that. And paracetamol and caffeine, just for the sake of understanding, I have taken. There are many components, many combinations which you can analyze. And A2 and A1 are the sample absorbances. These are the absorptivity values. You can calculate the concentration of one of the components first, followed by the second component, and then provided this is the first one, first requirement, and then you apply the formula and get the concentration. Now, the absorbance ratio method is another. What if the lambda maxes are not very far off? In that case, apply this absorbance ratio method. Absorbance ratio method depends on, or the whole concept is built on a very simple fundamental fact, that ratio of absorbances of a compound at any two wavelengths is constant, irrespective of the concentration. That means if I measure the absorbance of 1 microgram per ml solution or 10 microgram solution, but if I take the ratio of that same absorbance at say 250 nanometer and 270 nanometers, that ratio, irrespective of the concentration, would remain same. This is what is the principle of absorbance ratio method. And this ratio is also used as a qualitative tool, especially in US pharmacopoeia. They say absorbance, well, the ratio of absorbance at 270 to 250 should be this, to identify as an identifying tool for some of the compounds, right? 270, maybe 272. I'm just giving up backpack values. It need not be those values, any value. That's it's used, and USP calls it as Q value. This is also used in this thing in calibration of usable spectrophotometry, especially for stray line using KCl solution. Now, how do we use this for quantification? In this, we see, right, there are two, the individual X and Y, and then this point where both of them have the same absorbance values, right? This point, these points, it can be many also, is called as iso-absorptive point. That means the absorbance values of component X and component Y is same at this wavelength, right? This maybe 220 here is called as iso-absorptive point. And in absorbance ratio method, we use that as the as the basis, right? And QM, and this is the formula which is used, and two wavelengths which are selected are the lambda max of the corresponding compounds that is, if it is Cx, lambda max of Cx is selected and isoabsorptive point. Similarly, if it is component Y, then the lambda max of Y is selected and the measurements are made at that wavelength. In this case, if we are looking at this is 210 and 230, and what was this is 220. No, sorry, not 220. It may be 213 also, right? So in this case, for X, if we consider that same mixture, then for X isoabsorptive point, one of the wavelengths would be 213, the other one will be 210, and those absorbance and absorptivity ratios are calculated, and then you have you get the concentrations here. Similarly, concentration of the second component. Now, geometric correction method is another geometric using geometric or the calculus tools are used, and mathematical in mathematics the calculus tools are used. It's a 3-point geometric correction which is commonly used, but you can use a number of geometric correction points. 3 is very simple to explain, that's why I've taken 3 points, and that's very generally used as well, because it's not all that easy when you use more number of geometric more number of points, but the more number of points would increases the accuracy of the method, no doubt. You can select any of these 3 wavelengths where the compound under question absorbs. Okay, now these are the absorbance values. Designate those wavelengths as 1, 2, and 3, and these are the absorbance values at those wavelengths, right? And Y and Z are the difference, numerical difference between A1 and A2 and A2 and A3, right? A1, A2 as a that is lambda 1 and lambda. A is the absorbance, but lambda, the wavelength at which this absorbance is obtained, lambda 1, lambda 2, and this is the wavelength that is this absorbance is lambda 3. So Y is lambda 2 minus lambda 1, and Z is lambda 3 minus lambda 2. Okay, and here again, V and W, we have them here in the formula. If you see, they are lambda 2, W is nothing but lambda 2 divided by lambda 1, and V is nothing but lambda 3 divided by lambda 2. Okay, and once we know these values, these absorbance values, without any standard or without any of these things, of course we can also develop some small computer programs for this. Your Excel would be more than enough if we are doing it in routine practice. But if it's only for, as a routine analysis, if it's only for practice, then with a piece of paper also you can do this calculations. They look complicated, but they become very simple when you keep this distance or the difference between 2 wavelengths constant. Like you select wavelength 250, 270, 290, the difference is 20 nanometers. Then the calculations becomes much simpler, and you can easily write this thing, right? And polynomial is another, orthogonal polynomials which can be calculated with the present computing capabilities, and the spectrum which I have showed you can be represented, need to be represented in terms of orthogonal functions, and then that is also done as a quantitative method, which are at higher order. Differential spectroscopy is another method that is also can be very easily applied in case of many drugs. Please remember, this is different from derivative spectroscopy. This differential spectroscopy is used where some variable would bring about change in lambda max of the compound. One of the simplest example I can give you is phenolphthalein, which most of us have seen, right? Phenolphthalein at pH values below 8 is colorless, and above 8 it is pink colored. So that obviously means that the lambda max of phenolphthalein at pH 8 onwards is different than its lambda max below pH 8. Okay, now this same property can be used for quantitative measurements. How is it done? The say given unknown is measured, its absorbance is measured at pH say 3, and then the pH of this solution is changed to pH say 8. This is 11, 13, okay, somewhere in 8.5. okay, pH is changed to somewhere in 8, where you have the absorbance, right? You have two absorbance values, and the difference between these two absorbance values plotted in the Lambert-Weir equation, that is ABC, and then you can calculate B is of course instrumental variable and calculate this. Sometimes this also for common compounds is delta A is, once you have the lambda of these two, the absorbance at this, absorbance at this, you can always calculate the absorptivity values at these these concentrations, and then the difference between these two absorptivity values would be delta A, and then B is path length is the concentration which we don't know, but this can be measured of the unknown solution, and concentration can easily be calculated. This is especially useful when the compounds, when the lambda max of a given unknown can be changed with some simple factors or simple variables like pH or temperature, etc. Complicated chemical reactions can be used, but then it adds to the variables. The chemicals or the reagents which are added may also interfere with the absorbance, and things may be slightly complicated. The next one, which again most of us commonly use, is derivative spectroscopy. Now, derivative spectroscopy is again cannot be used indiscriminately. Derivative spectroscopy is preferred to be used when the absorbance of two compounds is highly overlapping, or when you have two absorbance bands within one another. There are two compounds, but both of them absorb. Say the second compound has an absorbance spectrum like this inside, the way I'm moving my cursor, it's inside, but ultimately when the mixture shows the absorptivity, it shows something like this. The spectrum would look like something like this, right? And only in such cases derivative spectroscopy is used. Now, derivative spectroscopy, first derivative, second derivative, third derivative, fourth derivative, we can use a number of derivative orders. There's absolutely no problem. But when you have odd number derivatives, you will have both positive and negative, whereas in case of even number, in odd number derivatives, the lambda max is denoted by 0 line, and in even number derivatives, the lambda max is derived by the highest peaks. That's either positive or negative, right? And how do we derivatize the spectrum? This is zero derivative, of course, all of we know. And first order derivative is small change with an absorbance with wavelength and absorptivity with wavelength. And similarly, up to nth order, we can go and get the derivative values, right? And yeah, this starts and ends with 0, the first order derivative, and lambda max is the 0.0 crossing is nothing but the lambda max. And Second derivative, you can see here again, this is the lambda max, and there are two satellite bands as positive and negative bands. There are multiple methods of obtaining the derivatives. Most of the present day instruments, especially the spectrophotometers, give the derivatives as it is, but of course otherwise by by various methods. The most simple is the mathematical relationship or mathematical derivatization is done. Even if the instrument is not capable of giving derivative spectra, you can derivatize the zero order spectra and use them, right? And no, why derivative spectra is used? See, something like a mixture like this, the compounds which show lambda max or show spectra like this. Of course, this will, the dotted line will not be seen in case of first order derivative, right? So, but actually, when they are taken individually, they have a spectrum like this. There's a lot of overlapping, and the component B is largely covered in the spectrum of component A. So, in such cases, the first order derivative spectroscopy would be very, very useful for us, and higher order derivatives make the difference all the more significant, right? Especially when the concentrations are very different and the interference cannot be overcome, or and your objective is not to quantify this, your objective is only to quantify this, eliminate the second component. In such cases, derivative would be very, very useful, right? Of course, derivative, there are formulae available, and this thing, but derivative spectroscopy is not very effective when it comes to the photometer, right? Photometer derivative, because they are not very sophisticated instruments. Spectrophotometer, the spectrum obtained from a spectrophotometer which contains gratings and PMT photomultiplier tube, the spectrum obtained from that, even if the derivative is done manually, which gives you a very good result, but if it is not a high end in the UV visible spectrometer or UV visible photometers, they don't give you very satisfactory results with derivative spectroscopy, right? And whenever you are looking at derivatizing the spectrum or using derivative spectroscopy as a technique, don't smoothen the curve. Most of the new instruments have an option of smoothing the curves. Say no, right? Say no. The sharp spakes would also give you details about the vibrational excitation stage, and they are more useful. They give you more reliable results, especially when you go for derivatization, than the smooth curves. So keep the smoothing to minimum, if possible zero, when we are using derivative spectroscopy, right? And with this, I come to the end of my presentation. If there are any questions, and then yeah, of course, it is very highly structured, the whole program, and then we have questions and things like that, which madam is going to organize. So with this, madam, I will stop. Thank you very much, and then we can proceed to the next part, whatever you have planned.
Okay, thank you very much, sir. Now we will head for the question answer session. So there are a few questions from the audience, sir. So
Okay, please go ahead.
first question, yes, sir.
Go ahead, go ahead.
Okay, sir. First question is that what is the difference between spectroscopy and spectrometry?
There's no
Actually,
difference.
yeah, because these two terms are used interchangeably, so they are asking that is there any difference between them?
No.
Okay.
Spectrometry is a old terminology.
Huh.
Old terminology, but there is no difference in between them as it is.
Okay.
Can I
Next
interrupt,
question.
Dr. Krishnamurthy?
Yes, sir.
Sir, why always we call mass spectrometry only? We don't call mass spectroscopy.
So
So
they
I
are
think it has
conventional.
something to do with light or something to do with electromagnetic radiation, because in mass we don't use that. Maybe nowadays they are using it intermittently, exchangeably.
Originally, they might have had something. That's possible.
Yeah. Yes. Thank you.
Thank you, sir. Next question is that why is quantitative analysis always done in absorbance rather than percentage transmission?
Can you please repeat that question?
Yes, sir. Why is quantitative analysis always done in absorbance mode rather than percentage transmission?
Okay. See, percentage transmittance, essentially the Lambert-Weir equation is derived in terms of absorbance values. So even if you measure percentage transmittance, ultimately you have to convert that percentage transmittance into absorbance to fit into Lambert-Weir equation. So that is why we, to be very precise, the instrument does not, an instrument cannot measure absorbance. The photomultiplier tube or the photoemissive tube, whatever is used in the instrument, measures only transmittance. It converts that transmittance from the intensity of incident radiation into absorbance and gives. That is why if you see the analog instruments, they have both options, percentage transmittance and percentage absorbance. So that is essentially, the whole concept, the Lambert-Weir law itself is based on absorbance. That is why we measure absorbance for the sake of convenience.
Okay, thank you, sir. Next question is, why spectrometer scans the wavelength from higher to lower side and not vice versa?
That is because of the instrumental limitation. Especially the monochromators.
Okay, thank you, sir. There is one more question, sir, that how absorptivity can be calculated with no reference value?
No reference value. Absorptivity itself is a reference value.
Okay, sir. I hope all the questions of the audience have been cleared. Thank you very much, sir, for answering all the questions in detail. Thank you, sir, for such a wonderful and insightful session. Now, we are heading towards the end of today's session. All the participants are requested to join the tomorrow's session sharp at 5 p.m. and the joining link have already been mailed to you and it will be different than today's. Thank you all again for your presence. With permission of our speaker and principal, sir, I would like to conclude the session. Please, sir.
Yes, madam. Thank you very much, Dr. Krishnamurthy. All your answers were up to the point and your explanation was also very good. And so was your presentation, and I hope the students have benefited from it. And we are awaiting tomorrow for another next very good session. Thank you very much.
Thank you, sir.
Madam, you can now, yeah, madam, you can now close the session, and tomorrow we will again start at 4:45. Thank you.
Okay. Thank you, sir. Thank you all once again. Have a good evening.
Yeah. Yeah.
And for